All right, we're going to take a look at a question that we didn't have time for in class, and going to make a short video of this. And this question is asking us to find all roots over the complex numbers and write in factored form. So we got a fourth degree polynomial, and since they say over the complex numbers, we may have some i's in there. So we're going to use the PQ theorem, the rational roots theorem, to find our possible rational roots. Okay, so our P is going to be the negative 117, and the Q is going to be just positive 1. And if I want to get my factors of 117, there's a divisibility rule for 3, and if I add up the digits here, 1, 1, and 7, that's 9, that's divisible by 3, so it is divisible by 3. So that helped me break it down. So 117 is going to be 1 times 117, 3 times 39, and 9 times 13. Those are the factors of 117. So that's where these are coming from. Okay. Again, just maybe for clarification, 117, it's 3 and 39, and then break it down from there. Okay. So we'll write all our factors. Plus minus 1, plus minus 3, plus minus 9, plus minus 13, plus minus 39, and plus minus 117, and then the Q is just plus minus 1, so that doesn't change our potential rational roots. So what we'll do now is we're going to try 1. That's kind of the convention here is we'll try 1 and negative 1 with the synthetic division. So we write down the coefficients. X to the fourth has a 1, 12x cubed has a 12, minus 4x squared has a minus 4, 108x has a 108, and negative 117. And all the powers are in descending order. We're going to put 1 on the outside, and we'll do the synthetic division. And we get a remainder of 0. Okay? So for the synthetic division, you bring down the 1. 1 times 1 is 1. 12 plus 1 is 13. And then remove the 13 here. 1 times 13 is 13. Negative 4 plus 13 is 9. 9 times 1 is 9. Added to 108 gives me 117. 1 times 117 is 117. Added to negative 117, we get the remainder of 0. Okay? So it tells me that 1 is a root, or 0, and that tells me that also x minus 1 is a factor. That's using the factor theorem. Okay? So what I have here is my remainder, my constant, x, x squared, and x cubed. So unless I can do some sort of factor by grouping, maybe I can, maybe I can't. This one I could have done factor by grouping, but we're going to do synthetic division again using the rational roots theorem. So maybe off to the side I did some scratch work and I found that 1, 3, 9, and their negative versions did not work. And I tried 13, it didn't work. We're going to try 13 with the synthetic, or negative 13 with the synthetic division. So I'm going to write down my coefficients from this here. The 1, the 13, the 9, the 117, and we don't need the 0 there. Okay. So doing that synthetic division, bring down the 1, negative 13 times 1 is negative 13. Negative 13 plus 13, this is a 13 right here. It kind of looks like it says is, but that's just my lovely handwriting there. So we get remainder 0. Negative 13 times 0 is 0. 0 added to 9 is 9. And then 9 times negative 13 is negative 117. We get a remainder of 0. This tells me that negative 13 is a root. So x plus 13 is a factor, and that's using the factor theorem. And we're home free now because what I have left is a quadratic, and I have many ways of solving quadratics. So I have x squared plus 9 equals 0. I'll subtract 9 from both sides, and I'll have x squared equals negative 9. Take the square root, don't forget the plus and minus, and the square root of a negative 1 is going to be I, so we get plus and minus 3i. Okay, so my roots I've boxed up are 1, negative 13, plus and minus 3i. So my factored form, and fundamental theorem of algebra says that I can do this over the complex numbers. I can break any polynomial up into a product of linears over the complex numbers. So it's going to be x minus 1, x plus 13, x plus 3i, and x minus 3i. So completely broken down. Alright, so this is probably the more involved example. We take a fourth degree, we break it down to a third degree, and then we break it down into a quadratic. Once we get into a quadratic, we have quadratic formula, rational, square root property, and a lot of times we can factor it.